right, Chapter 11, Lesson 3, we're talking about area of polygons. So we already know some familiar areas, square, rectangle, triangle. We're going to use the triangle, actually. The reason we spend so much time on it is because it's such a basis for other things. We're going to see that right here. So if someone asks you off the top of your head the formula for area of a rhombus, I don't know that many people know it, or a kite. So let's see where it comes from. So first of all, let's see how they have this kind of bolded in red. Let's find the area of just this triangle. We know how to find the area of a triangle. Area of a triangle is going to be half the base times the height. So in this case, my base, they're representing with this length here, and they're calling that D1. We're going to talk about why that is in a moment. Now my height is this portion here. Now they are calling this entire distance D2, which is why there's that arrow saying that this top portion, this portion of my triangle is only 1/2 D2. Okay, so lots of variables flying through here. This isn't really critical. I'm just showing you where the formula comes from. So if you even want to move it forward a little bit in the video, by all means do so. Anyways, though, whoopsies, we have 1/2. I'm bringing this down from my area to see how I get it. My base is D1. My height is 1/2 D2. All right, 1/2 times 1/2 is 1/4. So I get 1/4 D1 D2. Now remember, this was only the area of the red triangle. That's going to be symmetrically equivalent right below it. So I'm going to multiply this number by 2. So 1/4 D1 D2 times 2. And we're going to get an answer of 1/2 D1 D2 for the area of this entire rhombus. Okay, now the same thing would happen over here when I would work through that, because it's the same setup. So if we just scroll down a little bit lower, hopefully those people that maybe skipped this are going to come back now. We see that exact formula that we just came up with. The area of a rhombus or a kite is 1/2 D1 D2, and that's what we just kind of calculated here. So if you're ever stuck and you're taking, I'm thinking like SAT, ACT, SAT Choose, anything like that, and you have a geometry problem, see if you can break it into triangles. So much relates back to triangles. Okay. Anyways, so that's the formula, 1/2. Now D1 and D2, just to remind us, this is a diagonal of a rhombus, and this is the diagonal of a rhombus. So you can imagine that D1 and D2 stand for diagonal. Okay, all right, let's try a couple. These ones should be pretty nice and easy. The area here is 1/2 D1 D2. I'll just write it this one time and not after that. So 1/2, it doesn't matter if you do 6 is the D1 or 8 is the D1 diagonal one, it's up to you. My diagonal 2 would be 8 in this case, so 1/2 of 6 is 3. 3 times 8 is 24. And don't forget to label it meters squared. Okay, the next one is going to be 1/2 of 10 times 7, or 1/2 of 35, or 1/2 of 70, which is 35 centimeters squared. All right, how nice was that, right? So now you can add area of a rhombus and area of a kite to your formulas that you know. Now it's going to get a little more involved. So now we're going to find the angle measures in regular polygons. This is key. It has to be a regular polygon. Let's think back about what that means. A regular polygon means that all of our sides are congruent and all of our angles are congruent. Okay, so my regular polygon, now this is not what's in your packet. I've covered up the one that they're showing because I kind of want to create what's there together. That is my regular polygon. Now what it is you can see it's inscribed. It's inscribed in a circle. It's inside of a circle. So if I make this my center point of the circle, right, I can go ahead and draw out a line here. This would be a radius of my circle, right? It's also a point that goes from the center to a vertex of my polygon. Okay, so that's where this terminology comes into play. It's called, I'll do it in green, the radius of a regular polygon. So you never really thought of radius related to polygon, but you can have that. And that's just when you take the center, so that's the other term, center of a regular polygon. Again, it has to be regular. But the center of a regular polygon, and you go to a vertex and a vertex. So this is our center, this is the radius. So this entire If I even make it a different color to emphasize it, this here is a radius, okay, of my polygon. Now there's this new word, and it's called the apothem, okay? So the apothem, let me write this in first. This is the radius, and so is this one. Now the apothem is when we take our center and we draw it perpendicularly to a side, okay, one of my sides. This right here is my apothem. So that's a new word. Okay, so that's whenever we take our center and we draw it perpendicularly to a side. Okay, alrighty. The last thing it says here, and talks a little bit about how you can use the term apothem, but a central angle of a regular polygon is an angle formed when two radii drawn to consecutive vertices of the polygon. So this here is a central angle. Just like we saw central angle with circles, right? If I kind of got rid of, I don't know if I can get rid of just that. I wanted to get rid of just the polygon. It might be tricky to do that. If I just got rid of that hexagon, I would just have a circle, in which case this angle that I'm writing in, whoops, that angle would be considered my central angle. Same thing, just central angle of a regular polygon. Okay, and so if I want to find what that is, I go ahead and divide 360 by how many sides it is. So in this case, I have 1, 2, 3, 4, 5, 6. I just said it's a hexagon. So to find what this central angle is, and that's this angle that I'm referencing right here, to find the measure of that central angle, I would do 360 divided by 6 and find that it is going to be 60 degrees. So this angle here is 60 degrees. Okay, now before we do any hard calculations, let's just make sure we understand that. Okay, all right. So I'm going to scroll down here. They're asking us to identify a few things. It says in this diagram, ABCDE is a regular pentagon. My voice and brain always goes to triangle. But ABCDE is a regular pentagon inscribed in circle F. The reason they have to say it's inscribed is because that means that the vertices hit on the circle, and that allows us to go ahead and conclude that that's not only the center of the circle, it's also the center of the polygon and everything else that follows. All right, find each angle measure. First one is the measure of angle AFB, this angle here. So this is a central angle, and we saw above we're going to do 360 divided by how many sides we have, which in this case it's a pentagon, so there are 5. Okay, all right, so 360 divided by 5 we know is 72, so I can just write that that's 72 degrees. The next thing they want us to figure out is the measure of angle AFG. So let's erase this. AFG is AFG, so it's half of that 72, so this is going to be 36 degrees. If you think about it, if I kind of redraw that triangle, this is B, this is F, this is G, this is A. If this whole thing was 72, and I know I'm dividing it, I'm bisecting the angle, so that's how I know that just this portion, AFG, just that portion is going to be 36, okay, because 36 and 36 makes 72. And then the last thing they want is the measure of angle GAF. GAF, so that's this angle in here. Well, if this is 36 degrees and this is 90 degrees, then all I have to do is either triangle sum theorem or one of the corollaries, and I find that this is going to be 54 degrees. Okay. All right, let's try one more of these, and then we're going to pause. And you'll there will be 2 parts to this lesson. Okay. So again, find the center. So identify the center. Point P is the center of that. Again, sorry, I jumped the gun. In the diagram, WXYZ is a square inscribed in circle P. So it's inscribed in circle P as a square. The center of the polygon is what they want us to find first. So it's point P. The radius, there's actually 2. We can say X or PX or PY. Those Y. Those are both radii of the circle. And the apothem, again, is when we take our center point and we draw it perpendicularly to one of the sides of that polygon. So PQ is my apothem. And then a central angle is going to be this entire angle. So it's going to be angle or ypx, either one. Now they want us to find those measures, so angle xpy, the measure of that, this angle here. So if I kind of redraw the triangle xpy, I'll draw in that this is point Q and that's a right angle. So right now what they're asking us for is xpy, this whole thing. Well, I'm going to do 360 divided by 4, and that gives me this is a 90-degree angle. And we know that in a square, our diagonals, which if I extended those, our diagonals bisect perpendicularly. So isn't it cool? Everything connects. Everything. All right, anyways, we're almost done with this portion. XPQ. Well, then this must be 45 degrees. And lastly, PXQ, that measure. PXQ, so that's this angle here, is also going to be 45 degrees. Okay? All right, we're going to stop there, pick up with the next video to continue on. Thanks, guys.